Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. Today's screencast, like most of my screencasts, will be about the reciprocal system, specifically the reciprocal system microcosmos database. I've already covered the Macrocosmos database in detail with the previous screencast. You can see this on the right side. So on the left side here, the Microcosmos database. In previous screencasts, I've covered solid-state interatomic distance, valence, specific heat, energy and entropy, thermal expansion, compressibility. No, excuse me. We're going to do compressibility today. And in future videos, I'll do all the rest of these. Now, I do recommend that you use a Xeon microprocessor for the Microcosmos database. It's not really necessary for the Macrocosmos database because it's not as computationally intensive as the Microcosmos database. But you can still get by with an i7 or i9 core, Intel processor or AMD. It's just that the Xeon processor will be faster, especially for specific heat calculations, energy and entropy, thermal expansion. But I'm using my desktop today, the i7-990X, which is the fastest processor you could buy back in 2012, but it seems a little slow now, but it's perfectly fine for this particular layout. Just to check what element or compound we're working with, it's best to go in interatomic distance because that comes up quickly. So here it is. This is iron. That's the one that I want to work with today. So I'm going to close that, and I'm going to press on compressibility. So take a little bit to load. So let's just hop over to the right side, the Macrocosmos database, and I'll just show you this. This covers the universe as a whole, galaxy clusters and groups, galaxy star clusters, stars, planets, moons, minor bodies, nebulae, gas and dust, events and voids, and it has a nice graphing program, and including for the space-time progression and gravitation and star properties. We'll come back to the Microcosmos database and we'll just have to wait for this to load. Just have to be a little patient. All the calculations here are ab initio, which means that they're completely theoretical calculations which can be compared with observed data. Okay, that wasn't too bad. That was pretty quick. Now the top line is the same as in the other layouts. The element, compound, or mix is here. We're dealing with iron, Fe, description iron. Form number is 1. Atomic or molecular weight is here. Melting temperature is here. These are the quantized thermal factors and compressibility factors. I refer you to my mentor's work, Basic Properties of Matter. My mentor was Dewey B. Larson, great scientist and engineer. He's the original developer of the reciprocal system. Now you can see here, basically you enter in the temperature and the pressure. The temperature is always, in this database, the temperature is always in Kelvin. So please keep that in mind. It's in Kelvin. And the pressure can be in dynes per centimeters squared, pound per inches squared, psi, atmospheres, kilograms per centimeter squared, which is Bridgman's unit. It's a little strange units, but he did a lot of work in compressibility, so that's why we have them here. You put in one of these values here, and the others will all calculate. Okay, so right now this is like 1 atmosphere. See that right there? Yeah, just notice the factors here. So this is a 1 atmosphere. Now, once you have those 2 points, temperature and pressure put in, T and P, then the program will calculate virtually everything else that you need. So, and by the way, down here it just assumes atmosphere, so you can see it's 1 atmosphere. But the real utility of this comes when you use very high pressures. But I just want to go through the different fields here. Now this is the internal pressure. again, dynes per centimeter squared, pound per inch squared, atmosphere, kilograms per centimeter squared. So they're right here calculated. Then the compressibility K, which is centimeters squared per dyne, so it's just the inverse. Here's the bulk modulus here. Modulus of elasticity, that's in tension. Modulus of elasticity, that's really in rotation, torsion. And then Poisson's ratios here. And you can put in the temperature and pressure. And here's the unit cell volume for the aggregate and at the molecular level. Slight difference, very slight difference. This is the volume for the volume at T when P equals 0 with no pressure. And then the density in grams per centimeter cubed here. Cohesive energy in kilojoules per mole for the aggregate and for on a molecular basis. Of course, 0, there wouldn't be any difference, but here, when it's 420, got that. And then you have the crystal geometric factor, which comes from the first layout in atomic distance, actually. It's the kg factor. That's the interatomic distance in angstroms. This is the interatomic distance at the temperature, and then pressure, so on and so forth. This is the internal pressure, temperature change pressure phi times the mean area of the crystal unit cell. So that's an interesting factor right here. And then these would be for various transitions. Apparently there are no transitions for iron, but there would be for some compounds. Now let's just see what happens if I change this. Let me just click into here. I'll take a little bit of time. Okay, and let's see, change this to 1. A million. Okay, it's still loading. You just have to be patient. Okay, I'm going to change this to 1 instead of 0.00001. Okay, click off of it. Now all this is going to recalculate. Again, you just have to be a little patient. So this will be 1,000,000 atmospheres. Again, with the Xeon processor, it would be definitely faster than the i7-99X, 990X, but it's all right. In the meantime, you can look at all the other fields on the screen here. Just get used to the layout. Okay, there we go. So notice that it changed it down here as well. And so now you can see that the cohesive energy is different. The density is, I mean, look at the difference here in density. So everything has changed as you would certainly expect it to. Okie doke. Well, I think that pretty much covers it. Down here, if there are transitions, then some of this is going to change. The AZY factors, that's the compressibility factors, will change. So you have to put in the new AZY factors here, and then it will calculate the internal pressure in kilograms per centimeter squared. That's Bridgman's units and in atmospheres, which is what I'm more comfortable with. There's some miscellaneous fields here: endpoint temperature, The initial S0 over 2.914 cubed, that's, 2.914, by the way, is the time region unit of the natural unit of space. And then the volume strain is changing crystal unit volume from the initial line divided by the initial volume, so that's the strain. And that's just the initial factor right there. Okay. And here's the Brunel hardness. Neither conventional theory nor that has yet a theoretical method to calculate the Brunel hardness, so this is just an empirical data point. Now, just to make this whole thing complete. All right, wow. I think that covers everything, so let's close out. So please study the reciprocal system and prove it for yourself. For the simplest possible treatment, please obtain my work, The Unmysterious Universe. 80 pages only, has all the concepts, many diagrams. It's really easy to read. I've gotten very good reviews on Amazon with it. Now, if you do want all the mathematics, and I mean all the mathematics, please obtain my work, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. 711 pages in the PDF file, 711 slides in the PowerPoint file, thousands and thousands of equations, diagrams, tables, figures. It'll take you months to go through. And then once you're fully up to date with Existence and Interactions, then you can get these 2 database modules. I've already gone through the different layouts here, and you can watch my screencast to look at the actual fields. My theoretical physics mentor, Dewey Larson, was also a theoretical economist, and I've made his work in economics also fully computational. That's my work, Optimal Economist, and Implementation of Larsonian Econophysics. I will eventually be doing some screencasts on that. But it completely supersedes Keynesian economics. It covers the microeconomics of individuals and business sectors, and the macroeconomics of whole countries and regions. So it's very comprehensive, very easy to use, very, very powerful. I compute all the financial ratios you need to make a decision as to whether or not to buy a stock. It's pretty amazing. It has lots of capability to do projections. Okay, well, that's it for today. Please, again, study the reciprocal system, prove it for yourself, and thanks for your attention.